kind of annoying way. The usual results of term-by-term calculus over series still hold, and because of that, we're able to define the usual elementary functions over in algebra and to derive their properties from calculus. The adding angles formulas for sine and cosine, if you look at some books, the argument which is given, it seems to necessitate the use of a complex unit, and I squared is minus 1, but that's just, that's not actually necessary to have an imaginary unit to do sine and cosine. The argument that's given in Theorem 6.18 on page 32, there is an argument there which shows how to derive the adding angles formulas for sine and cosine just through calculus alone.
Which equation are you on?
Well, actually, it's theorem. It's leading this theorem 6. Actually, I think 6.18.
Okay.
Is.
I did a big scroll.
So theorem 6.18 on page 32. It says that if you've got a function on a connected subset of the algebra and it satisfies f prime prime equal to minus f, and if it's 0 at 0, and if the derivative at 0 is b, then it follows that it's a b times the sine in the algebra. So basically this is uniqueness of sine as a solution to the differential equation, f prime prime equal to minus f. And then theorem 6.19, I think, is uniqueness of cosine as the solution. Well, this is actually just the general solution. If you have f of 0 is a and f prime of 0 is b, then a solution to f prime prime equal to minus f, then it is f of z is a times cosine plus b times sine. So.
But then why did we never go how that worked? I feel like in calculus 2 they just said sine and they just gave us a list of derivatives, but
right. Well,
that's such an interesting property that that you take two derivatives and you get the original function back just with the negative.
And that forces it to be sine and cosine multiple. Now here we have definitions of sine and cosine in terms of power series, right? So although I think if you study these arguments, it may actually not even really use that so much as it uses, well, like basically it defines a u and a v, and it works with those to derive various identities. It's actually kind of more in the spirit of the proof that cosine squared plus sine squared is 1. I believe, and I don't see the reference right here, but I think we found these arguments in Pfaffenberger's. I'm sorry, I just like that. Or is it Pfaffenbaugh? Johansson? There's a Dover book on analysis. It's like the most popular one, where I think we found these arguments. I think the argument which is in Dating Rubin uses I, so we didn't want the argument for sine and cosine to necessarily use I, such as I squared is minus 1, because we don't have that in the arbitrary algebra.
Yeah.
We do have is calculus, the power series. So, but anyway, there it is. And then ultimately, theorem 6.20 is the adding angles formulas for sine and cosine.
Yep.
But again, Daniel Fries was able to adapt the arguments that are these proofs. There were things we found in mainline analysis undergraduate books. They just need to be tweaked a little bit to adapt to what we have. Now, so that brings us to the n-pythagorean theorem at last. And so the first thing I have to do is to define what I mean by Mr. Owen, the special functions of the algebra. And so I've actually already started talking to you about that.
Yeah.
The special functions of these three hyperbolic numbers are Larry, Moe, and Curly.
Yes.
The special functions of the complex numbers are cosine and sine. The special functions of the hyperbolic two numbers, cosh and sinh.
Yep.
The special functions of the dual numbers are the constant 1 and the function y. It's kind of boring. But let's see here. and that's what this section says, but theorem 7.3 says if you have a n-dimensional algebra generated by epsilon, then there exist unique functions on the reals such that,
T, epsilon T, F1 T, F1. Whoa, that's cool.
right, and so what I'm saying is those functions are unique, and those, in fact, are what we're going to call, well, these aren't the real functions, so I gotta be careful here.
I told you I was going.
You told me,
Yeah, don't sit on Benjamin in your chair.
I'm just putting off my socks.
so those are functions, those are functions which are defined on all of R, and in fact, each one of them, these are not only functions F1, F2, I'm supposed to use, I keep forgetting I need to use big N because of my series sequence of, these are entire. What does it mean if they're entire? If they're entire in R, that means that you can uniquely extend them to the whole of the algebra. So like Larry, Moe, and Curly, I could just as well think about them as a function of a 3 hyperbolic variable if I wanted. And this, if you had already had complex analysis, the story is somewhat familiar with complex analysis. Euler's identity, we start with cosine and sine on the reals, but then you think bigger. You think about cosine of z, and you think about sine of z, where z is a complex variable. These are well-defined things. In fact, cosine and sine are entire functions on the complex plane, because the Maclaurin series in the complex sense converges on the whole of the complex plane because it's got still the same coefficients as the corresponding real series. But complex sine and complex cosine have other features that are unfamiliar.
Yeah.
Like, let me show you. Cosine, so we can, this is cosine of x plus iy, right? So that's like cosine x, cosine iy, minus sine x, sine iy. Okay, so think about what's cosine of iy. It is 1 minus 1/2 iy squared. All right, remember I to the 4th is 1, right? I squared is minus 1. So that's 1 plus 1/2 y squared plus 1/4 factorial. In short, cosine iy is cosh y. So this cosine iy is actually cosh y.
Yep.
And what's going to happen with the sine of iy?
Cinch.
Right, you get iy, then you get minus 1/3 factorial iy cubed, right? So it's going to flip the minuses to pluses, but there's also an I that factors out. So I think this is going to be minus I sine x sinh y. So just to give you a sense of what's kind of the weirdness of this, which is familiar to any student of complex analysis, like the modulus of cosine z, right? So it's the square root of this squared plus that squared, right?
Yep.
So I'll write the square root. It's cosine squared cosh, good grief, cosine squared x cos squared y plus sine squared x sin squared y.
You feel like something should pop out. Something should go to 1, but it doesn't.
Yeah, I guess I can rewrite that as 1 minus sine squared x cos squared y plus sine squared x sin squared y. So what happens? I get cos squared y, right?
Mhm.
Plus sine squared x times what? Sin squared y minus cos squared y, right? But remember, cos squared minus sin squared is 1, right?
Mhm.
So this is really cos squared y minus sine squared x. And it's kind of a nice formula, whatever. Plus, no, minus. Man, I feel like I did something wrong here. You got that. Oh, it's fine. I was worried that this could be negative. This is the length squared of a complex value, right? So it should be negative. But the thing is, this is real sine.
Yeah.
So it's at most 1.
Mhm.
So this could be at most like minus 1. What is the smallest cosh can be? Cosh is at
1.
at least 1.
Yeah.
So this is at worst
Was 0.
0. How big does it get though? You're like, well, cosine is bounded by 1 and minus 1, right?
Yeah.
Not complex cosine. Complex cosine can get as big as this gets. This is cosh.
And
That
cosh.
gets as big as you want.
Yeah.
So complex cosine is unbounded.
Mhm.
Complex sine is unbounded. However, even though that's true, it's still the case that cosine squared z plus sine squared z is equal to 1. See, they're unbounded in such a way that they always have squares which add to 1, and yet their length, the length of cosine z or sine z can be as big as you want. However, when you restrict these functions to the real line, they're at most 1 or minus 1. I mean, their values are stuck between plus or minus 1 and the real value. You know? Cosine, complex cosine and sine restrict to real functions on the real axis. So this is interesting, right?
Yeah.
Okay, so
No.
if you have an algebra which is generated
This one?
by a generator, then you can look at these special functions of the algebra. And I've showed you some examples, right? Variable curly, cosh, sine, cosine, these are all
There you
special
go.
functions. Because the algebras we were talking about, they have a single generator.
Watch you doing it.
Like I generates the complex numbers, or epsilon generates the null numbers, or j, 1 and j squared equal to 1, or j cubed equal to 1. These are one generator algebras, so this is a well-defined.
Mhm.
Right. So, what else can we say about these special functions? Well, so I work them out, like the Larry, Moe, and Curly, I call F1, F2, and F3
Mhm.
in equation 115. Notice there that I'm looking at the algebra variable.
Yeah. Oh yeah.
And then likewise for the 3 null numbers, you end up with 1 z and 1/2 z squared as your special functions of that algebra. And then section 8 is about the n trigonometric and n hyperbolic functions, which is just basically giving more systematic naming as opposed to Larry, Moe, Curly.
Mhm.
And so he defines cosine sub n and sine sub n comma p. Because there's like, in his view, there's like 1 cosine, but there's n minus 1 sines for the algebra generated by I to the n equal to minus 1, and j to the n equal to 1. The n hyperbolic numbers give you there's a 1 hyperbolic cosine in Daniel's view,
Mm-hmm.
and there's n-1 hyperbolic sines. In the sense of like what he's saying, it's like Larry is the 3 hyperbolic cosine,
Mm-hmm.
and Mo and Curly, these are the 3 hyperbolic sinus. It's just a nomenclature, it's just a labeling, definition 8.1. But more than that, he proves in equation 120 that there's differential relations between these, like derivative of the nth sinh gives you, go back to the cosh,
Mm-hmm.
the derivative of the cosh gives you the first sinh, the derivative of the first sinh gives you the second sinh, the derivative of the second sinh gives you the third sinh, and this is a connection, term by term differentiation of these sort of functions, because differentiation like shifts the coefficients to the next type basically. And of course those are the special functions of Cn or the special functions of Hn. And there's the proof is sort of mundane, but there it is on page 37. And so that's the backdrop for section 9, which is on Pythagorean functions. So we're looking at an algebra which is generated by a single thing. And so we can look at the matrix that's represented by Z. And I think we're gonna let the algebra be Rn.
Okay.
No.
And we're going to, I think, have at least some of these, of course, have E1 equal to the identity, where the formulas are nicest, right? So there's the regular, like example 9.1, regular representation of complex numbers. 9.2, regular representation of the n hyperbolic numbers. Equation 124. So that 123 is an n by n matrix. I just was being lazy and not like expanding it out. You know, 124, there's the regular representation of a 3 hyperbolic number, right? We looked at this before. Definition. So if we have a algebra, which we're looking at as Rn, with basis 1, j squared all the way through to jn minus 1, we define the real Pythagorean function by, here it is, so I'll say PA of t is equal to the determinant of e to the jt, j e to the jt, j to the n minus 1 e to the jt. Then, extend this to A to define Pythagorean function on A. So like PA is a function from, originally it's a function from the reals to the reals. And I'm arguing its entire, well, I guess I'm not arguing that, but anyway, I've defined it to be that, and then I say that the Pythagorean function of A is a unique extension of this real. I guess that definition begs the question, how do I know the extension is unique? But I may have actually neglected to prove that in this paper, but I do think it's true. I mean, I'm quite sure it's true. In any event, so let's look at this real Pythagorean function, all right? So example 9.4, let me just start showing how this fleshes out here. So PC, right? Determinant of e to the IP, I e to the IP, right?
Mm-hmm.
So that's the determinant of cosine t, sine t, and then minus sine t, cosine t. e to the it, of course, is what? It's cosine t plus I sine t, right? Or this formula?
Yep.
So what is this?
What's that? I mean, you just,
Mommy.
So we got cosine squared t plus sine squared t, right?
drop t. Not drop t, but it's just t.
Just t?
Yeah, because sine squared plus cosine squared.
Oh, it's 1, but all right, this is identically equal to 1. But my point is, this is the Pythagorean, this is the complex Pythagorean function and its extension to the complex numbers. If you want me to put it tilde on it or something, whatever, it's still cosine squared t plus sine squared t. So you just replace the t with the algebra variable, that's the extension, all right? And now it's no longer real value. Right, the extension need not be real value. It will be real value when we restrict it to the real numbers, of course, but, and as you pointed out, it is identically equal to 1. What happens when we look at the Pythagorean function for the hyperbolic numbers?
I feel like it'd be very close, but it'd be plus or minus. Because you don't get that sign.
Right.
Minus
So,
sign.
yeah, for hyperbolic numbers, we have e to the jt is cos t plus j sinh t.
Oh, which makes sense, yeah.
So when we look at
Then it'd
p
still be 1.
ht, we get determinant of e to the jt, j e to the agt, right? And really, this is just the matrix representation
Yeah.
of that, you know?
Yeah.
But yeah, that is cos t, sinh t, cos t, and like you said, minus 1, right? So you get cos squared t minus sinh squared t for that. But what do we know about cos squared minus sinh squared? Well,
1.
it's identically equal to 1. So what is the n-Pythagorean theorem? The n-Pythagorean theorem is just the claim that PAZ is equal to 1 for any such algebra.
Oh.
Now, if j to the n, it's an algebra of the form that the generator to the nth power is equal to the constant. If that constant is 0, the theorem is true, but it just ends up being 1 equals to 1, so it's not really that exciting. Example 9.7 shows that. On the other hand, if you look at what this theorem says for the 3 hyperbolic numbers, right? Equation 128, we've got that Larry cubed plus Mo cubed plus Curly cubed minus 3 times Larry Mo Curly is identically equal to 1.
That's nice.
Right. Now that is not a theorem that I would have known. But you see that the n-Pythagorean theorem, it says that the usual Pythagorean theorem for sine and cosine, and the usual Pythagorean for cos and sinh, and also this tower of similar identities for special functions of algebras. It gives you this whole list of identities.
Yeah.
Because we can make a proof for this theorem, which is independent of your choice of algebra. All that's needed is that it's an algebra of the type j to the n equal to 1. Now the proof. So I didn't discover this. This was something that Daniel, I think it was Daniel Fries who noticed this. And then I found a way to prove it. So like, here's the proof from section 10. Let's see here.
So you just noticed a pattern that everything kept going to 1.
Notice what?
You noticed that whenever you found the Pythagorean theorem, it always equal 1.
Right. Yeah, he noticed that because we were deep into studying exponentials and trying to understand like their component functions, what they looked like, what their properties were, and in the midst of proving those like identities about connecting derivatives of sinh and cosh and all that stuff.
Yeah.
I think just popped out at him. You have to ask Daniel for the specific history. Like, I don't know exactly when he thought of this, but let's see here. Let me look at the proof here. All right, so yeah. Huh. I do feel like I haven't actually proved that these are entire functions on the reals. There is a bit of a gap. I mean, I actually do think that they are entire because essentially what's going on is you're playing with the exponential, and so the coefficients of the exponential is like 1 over factorial, and then you're like picking off subparts of that. So the fact that you're just like dealing with like things that are descending from 1 over n factorial, it's going to almost certainly make these things entire, the series constructed from these coefficients entire, because you're like sampling from the exponential, which is entire, but that's not exactly the proof. Anyway, here's the proof of that theorem. So we have PA of t is the determinant of that, right? So what I'm going to do, Audric, is I'm going to write I'm going to write that as like the sum I1, I2, da da da, In of epsilon I1, I2, In, and then Fi1, Fi2, Fin. So what you're looking at here, this is just the formula for the determinant in terms of that Levi-Chizita symbol. I think I've shared with that before. Showed you that before. Now, so when you differentiate with respect to t, you basically, these are all functions of t, right? So what I'm saying is, this one is f1.
Yeah.
This one is f2. This one is fn. All right. And so these are constants. They're 0, -1, or 1.
Yeah.
And when you differentiate this, you can just pull the sum out by linearity. And pull the Levi-Chizita out, because it's a constant. And then you're looking at the derivative of this product, right? So then I'll write it this way. Then it's the sum let's say j equals 1 to n of f I1 dot 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 f I j hat, let's say, Fin. So what I'm saying is, take the list, delete the jth one,
Okay.
and then differentiate the jth one here. That's the product rule.
Yeah.
All right. And then I can write that as the sum. I can pull the j out here. And I've got my sum over I1 to the In. Epsilon I1, I2, And then I've got fi1, da da da, fij hat, da da da, fin, and then dfj dt. But let's look at that. What is dfj dt? You're looking
You
at,
said something over here. What was it?
yeah, well, this is just, so f sub j is,
Uh-huh.
it's j to the, oh, well, sub j, not bad. K, can't use j as an index here, I'm a dummy. K, right? F
And
sub k,
oh, yeah, it's N. That's K.
yeah.
That's K. Okay. No, DFK. Okay. It's okay.
So that's j to the, j to the k minus 1, right? E to the jt. So this is just what, this is the formula for f sub k.
Yeah.
Now, the rules of calculus over the algebra are just what you'd expect. They allow you to pull the j out because it's constant, and the e to the jt just differentiates as j e to the jt. So this gives us j to the k e to the jt. Right? But that's another one of the f's. It depends, right? This is equal to, you know, this is equal to j times f k minus 2, or is it k minus 1? No, it's jfk, right?
Alright.
Whatever. No.
Don't you listen to T? Like you pull the JK one out, but if you differentiate E to the JT, when JT come out, that just
Well, you get e to the jt times ddt of jt, which
Yeah.
is j to the jt. I mean, so like the differentiation with respect to t, if we differentiate jt, that just gives you j.
Yeah. Oh, I thought you were differentiating E to the JT, not the J.
Well, we are differentiating e to the jt, and so like ddt e to the jt by the chain rule is e to the jt, because it's exponential differentiation of itself again, times, because of this,
T.
yeah, j times ddt of jt, which is just j again.
Yeah. But yeah, never mind. I'm with you. Yeah.
So,
J plus is for
curves. So what I'm trying to get at here is that if I, independent of my knuckle brain inability to enumerate again, the point is this is it's not fk, it is like the next one. See,
K plus one.
if this was j, this becomes, it differentiates, it gets me to the j squared.
Mm-hmm.
If it's 1, it gets me to the second column.
Yeah.
If it's the last one, it gets me j to the n,
Yeah.
which is a multiple of the first column.
Yeah.
The point is, this is always a linear multiple of one of these.
Yeah.
But this is the determinant
Mhm.
of a matrix then, which has a column repeated. Therefore, everything here is 0,
Yeah.
which means the derivative is 0, which means that this is a constant function, which is why you get the Pythagorean theorem. But I thought that was so cool when Daniel first found it. I was like, Wow, this is so neat. We can get the identity for sine and cosine and for cosh and sinh all from one unified idea. But I'll show you next the differential equations. This same universe of ideas we're going to use to solve an arbitrary differential equation over the algebra, a constant coefficient